NASA aimed the most powerful telescope in history at the edge of time and saw what shouldn't exist: Michael Brown. According to the prevailing theory, 13.8 billion years ago, everything came into existence from a colossal explosion originating from a point smaller than an atom. However, the latest observations from the James Webb Space Telescope, JWST, have revealed galaxies to the scientific community that were already mature at a time when the universe should, theoretically, have been in its infancy. Scientists are observing stars where heavy elements formed long before the cosmos had sufficient time to cook them. Massive black holes exhibiting incredible growth rates have been discovered in the early universe, alongside structures so perfectly organized that their existence in a chaotic young universe seems impossible. The most powerful telescope ever built by humanity was not initially designed to disprove the current story of the universe's origin, but it appears that is precisely what is happening. The James Webb Space Telescope, a $10 billion project, took 30 years of meticulous work to build. Its purpose was not merely to capture better images of space. Scientists had a specific objective: to confirm the absolute validity of the existing theory of cosmic creation. For decades, the scientific community adhered to a simple concept: the Big Bang occurred 13.8 billion years ago, followed by a 400 million year period of cosmic darkness as the first stars slowly formed. These early stars were presumed to have a simple composition made exclusively of hydrogen and helium. Galaxies were expected to grow gradually, chaotically, over billions of years, undergoing countless collisions and mergers. This timeline was not just a theoretical construct, it was the foundation of modern cosmology. Every textbook, every documentary, every explanation of how we came to be relied on this sequence of events. The James Webb Space Telescope was conceived as the primary witness to validate this theory. With its infrared vision, it could peer into the cosmic dawn and show us those very first primitive stars struggling to ignite in the profound darkness. Scientists anticipated seeing a chaotic, turbulent universe slowly organizing into the cosmos we observe today. The telescope's mirrors were polished to the highest degree of perfection, and its instruments calibrated to detect the faintest echoes of ancient light. The scientific community was preparing to celebrate a triumph, as the observations were expected to confirm what computer simulations had predicted for decades. The early universe was supposed to appear young, disorganized, and as chaotic as one would expect from a cosmos just beginning its existence. However, when the James Webb Space Telescope opened its golden eye and gazed into the beginning of time, it did not find the expected confirmation. Instead, it discovered something that made astronomers question everything they thought they knew about cosmic history. The telescope, intended to confirm the prevailing theory of the universe's origin, may instead be poised to completely dismantle it. The data obtained challenges not only the details of galaxy formation, but also the entire timeline of cosmic evolution. The implications of these discoveries extend far beyond astronomy. If our most fundamental story about reality is flawed, what does that mean for physics, philosophy, and our place in the universe? The discoveries yet to be made from the James Webb Space Telescope's data may force us to rewrite the very first chapter of existence. This, however, is merely the beginning of what is being revealed to us from the cosmic dawn. According to current understanding, 400 million years after the Big Bang, the universe should have been a cosmic wasteland. To put it in perspective, imagine the entire history of the cosmos compressed into a single year, and we are observing events on January the 2nd. At this point, galaxies should have been tiny, primitive clusters of the very first stars. Yet, the James Webb Space Telescope has discovered massive mature galaxies that appear to have existed for billions of years. These are not small groupings of nascent stars struggling to survive. Scientists are observing galaxies with masses equivalent to 100 billion suns, perfectly organized into spiral arms and central bulges. For comparison, our own Milky Way galaxy took over 13 billion years to reach this level of development. Nevertheless, galaxies have been found that somehow achieved this complexity when the universe was barely out of its infancy. The data obtained does not align with existing theories. Computer simulations indicate that galaxies of such mass require at least 2 billion years to form through the slow process of merging smaller galaxies. But we are seeing them when the universe was only 400 million years old. This is akin to finding a fully grown oak tree in a garden planted yesterday. Dr. Ivo Labbé from Swinburne University called these discoveries galactic monsters that should not exist. His team found galaxies so massive that they contain almost as much matter as all the stars that were supposed to exist in the entire observable universe at that time. The mathematical calculations simply do not reconcile with our current understanding of cosmic evolution. Even more surprising is the ordered appearance of these stellar systems. The Big Bang theory posits that young galaxies should be chaotic and shapeless, gradually acquiring structure under gravitational forces over vast periods. However, the James Webb Space Telescope shows us galaxies with distinct spiral arms, central supermassive black holes, and organized regions of active star formation. All these features typically take billions of years to form. This discovery presents astronomers with a complex dilemma. Either our understanding of the speed of galaxy formation is fundamentally wrong, or the accepted chronology of the universe's development requires a serious reevaluation. Some scientists are beginning to discuss alternative theories that could explain these observations. However, adopting such alternatives means abandoning a significant portion of the knowledge we have accumulated about the universe. The implications of this discovery extend beyond mere galaxy formation. If large galaxies existed in the early stages of cosmic development, they would have profoundly influenced the entire structure of cosmic evolution. The gravitational impact of these monster galaxies should have left traces throughout the universe, which, however, are not detected in other observations. Nevertheless, the body of evidence indicating the reality of these impossible galaxies continues to grow. At the very beginning of the universe's existence, only 3 elements were known: hydrogen, helium, and a trace amount of lithium. All other elements in the periodic table were supposed to form within the nuclear reactors of stars and be dispersed into space after their demise. This process takes a very long time, billions of years. However, the James Webb Space Telescope is detecting heavy elements in galaxies that formed when the cosmos was still very young. Imagine a star as a cosmic kitchen. It starts with simple ingredients, hydrogen and helium, and gradually cooks them into heavier elements through nuclear fusion: carbon, oxygen, silicon, iron. For all these elements to form, several generations of stars must exist. The first stars had to live their lives, explode as supernovae, and scatter heavy elements into space before the next generation of stars could form planets and more complex chemical compounds. This stellar cooking process can be compared to a cosmic assembly line that cannot be sped up. The most massive stars burn their fuel quickly and explode within a few million years. But even the fastest cosmic assembly line requires hundreds of millions of years to produce a significant amount of heavy elements. A universe that is only 400 million years old simply did not have enough time for this process to occur. Nevertheless, spectroscopic analysis of these early galaxies shows clear signs of oxygen, carbon, and even heavier elements like silicon and magnesium. The concentrations of these elements are not negligible, which could be explained by unusually rapid stellar development. We are observing a large amount of metals, indicating that several generations of star formation and death have already taken place. Dr. Emma Curtis Lake, who led some of these observations, reported the detection of galaxies with metallicity comparable to much younger systems. Spectral lines cannot lie. These galaxies contain elements that should not have existed in such quantities for billions of years of cosmic evolution. This discovery creates a whole series of problems for our cosmic chronology. If heavy elements existed so early, then planet formation could have begun much sooner than anticipated. Rocky planets, like Earth, require these heavy elements to form. The implications of this discovery for understanding when the first life in the universe might have emerged are simply astounding. Some astronomers suggest that the very first stars might have been much more massive than we previously believed, burning their fuel and creating heavy elements at an unprecedented rate. Other scientists propose that the star formation process itself might have been different in the early universe than it is today. However, both explanations require a revision of fundamental ideas about stellar physics. The elements detected by the James Webb Space Telescope simply should not have existed at that time, but they are there, recorded in the light of ancient galaxies, challenging everything we knew about cosmic chemistry. The next problem discovered seems relatively simple compared to the previous one. Imagine trying to erect a skyscraper in the middle of an earthquake, blindfolded. This is roughly how galaxy formation was apparently supposed to occur in the early universe. Cosmic space was a swirling chaos, filled with dark matter and gas colliding in random encounters. Galaxies were assumed to grow slowly and haphazardly, undergoing countless mergers over billions of years. However, the James Webb has found galaxies that appear as if they were designed by a cosmic architect. Previously, the Hubble Space Telescope had already shown that distant galaxies look more chaotic and disorganized than nearby ones. This seemed perfectly logical. By observing deeper into space, we saw galaxies in their adolescent stage, still growing and forming. The James Webb was expected to look even further back in time and see cosmic infants uncertainly growing in the dark. But instead, it found galaxies with clear spiral arms, organized central bulges, and structured star formation processes. These features require a delicate gravitational balance and billions of years of calm evolution to develop. In our own cosmic neighborhood, only the most mature galaxies exhibit such perfect organization. And yet, these galaxies existed at the cosmic dawn, astonishing in their complexity. Dr. Stephen Finkelstein from the University of Texas figuratively called these discoveries the finding of adult galaxies in a cosmic kindergarten. This level of organization contradicts the prevailing theory of hierarchical structure formation, which posits that small objects merge to form larger ones over cosmic time. It seems these galaxies completely skipped their chaotic childhood. Particularly puzzling are the smooth disk structures. In the modern universe, galactic disks form through a complex process where gas settles into rotating structures over hundreds of millions of years. In the early cosmic history, frequent mergers and chaotic conditions should have prevented such delicate structures from surviving. Nevertheless, the James Webb shows pristine spiral patterns that look as if they have never been disturbed. Even more astonishing are the central supermassive black holes, which appear perfectly coordinated with their surrounding galaxies. In the modern universe, close relationships are observed between the masses of black holes and the characteristics of their host galaxies. This correlation forms over billions of years through complex interactions between star formation and black hole growth. The detection of such coordination in young galaxies indicates the existence of processes that remain unknown for now. These discoveries challenge the entire concept of cosmic evolution. If galaxies can organize so quickly, then our understanding of how structure forms in the universe needs a fundamental overhaul. The smooth, organized galaxies discovered by the James Webb Telescope should not have existed for billions of years yet, but their perfect spiral arms lead us to an even stranger discovery related to rotation speeds that seem to defy the laws of physics. Galaxies rotate like cosmic hurricanes, held together by the gravitational influence of dark matter halos that surround them like invisible cocoons. The faster a galaxy spins, the greater the mass it requires to avoid being torn apart. This relationship between rotation speed and mass is one of the most robust laws in astronomy. However, the James Webb has discovered ancient galaxies rotating so rapidly that they should have ripped themselves apart billions of years ago. When astronomers measure the speed of stars moving within galactic disks, they can accurately calculate the galaxy's total mass. This is akin to observing cars on a circular racetrack. The faster they go without flying off the track, the steeper the banking must be. In galaxies, this banking is created by gravitational mass, primarily in the form of dark matter. The problem is that these early galaxies are rotating at speeds that demand dark matter halos far more massive than anything observed in computer models of structure formation. Some galaxies are spinning at 300 kilometers per second, whereas calculations suggest their speed should be limited to approximately 150 kilometers per second. This is like a motorcycle entering a sharp turn at twice the speed that should send it crashing into a wall. Dr. Claude-André Faucher-Giguère from Northwestern University, studying these rotation curves, called them impossible within existing galaxy formation models. The dark matter halos required to stabilize such rapid rotation would be so massive that they should dominate all surrounding space. However, no evidence of such gigantic halos in the cosmic Webb structure has yet been found. It is astonishing how quickly these rotation patterns were established. In the modern universe, galactic disks gradually acquire their rotation speed as gas settles into stable orbits over hundreds of millions of years. However, it appears these ancient galaxies reach their maximum rotation almost immediately after their formation. This can be compared to an ice skater executing a perfect pirouette from their very first seconds on the ice. The laws of physics become even more complex when considering the conservation of angular momentum. As galaxies form from collapsing gas clouds, they should gradually spin up as they shrink, much like a figure skater pulling their arms inward. However, the rotation speeds recorded by the James Webb Space Telescope indicate that these galaxies initially possessed far greater angular momentum than the cosmic web could have provided. Some scientists propose unusual solutions, including modified gravity or alternative dark matter models. Others suggest that the formation of early galaxies might have involved processes we do not yet understand. But every explanation requires either abandoning established physical theories or acknowledging that the early universe operated under completely different laws. These rotating galaxies lead us to an even more astonishing discovery. Collisions that occurred before galaxies seemingly should have existed. Galaxy mergers are cosmic catastrophes unfolding over hundreds of millions of years. When two galaxies collide, their gravitational dance creates tidal tails, stellar streams, and distorted structures that astronomers can recognize as clues at a cosmic accident scene. The James Webb Space Telescope has found this evidence in galaxies that formed when the universe was so young that collisions should not yet have been possible. The timeline problem is quite severe. According to our models, the first galaxies were tiny, isolated clusters of stars scattered across vast distances. They resembled cosmic hermits, too far apart and too small to interact significantly. Large-scale galaxy mergers were not expected to begin until the universe was at least 1 billion years old, when structures became large enough and close enough to gravitationally influence each other. Nevertheless, the James Webb Space Telescope shows us clear signs of mergers in galaxies that formed just 400 million years after the Big Bang. We see tidal streams of stars pulled away from galactic nuclei, dual cores indicating recent collisions, and asymmetrical structures that could only arise from gravitational interactions between massive objects. Dr. John Silverman of the Kavli Institute, analyzing these early merger signatures, describes them as finding car accidents in a world where cars hadn't been invented yet. The morphological features leave no doubt. These galaxies definitely collided with other massive systems. However, the cosmic timeline suggests that such collisions should be impossible at such an early stage in the universe's history. The discovery becomes even more intriguing when considering the frequency of mergers. In the nearby universe, major galaxy mergers occur relatively rarely. A galaxy like the Milky Way might experience one significant merger every few billion years. But in these early observations, signs of mergers are found in almost every galaxy the James Webb Space Telescope examines. It's as if the young universe was experiencing an epidemic of collisions. Even more complex is the scale of these ancient mergers. We are not observing small galaxies engulfing tiny companions, but rather large mergers between systems that are already massive and well-developed. The energy required to disrupt such large galaxies and then reorganize them into the structures we observe should be released over billions of years. Yet, We see the consequences when the universe was only 500 million years old. The implications of these discoveries impact our understanding of cosmic evolution. If large-scale mergers were common at such an early stage, they should have triggered powerful bursts of star formation and fed central black holes at an unprecedented rate. This should have left observable traces throughout the universe, which we simply do not see in other measurements of cosmic history. Some astronomers are beginning to question whether our fundamental timeline for structure formation is fundamentally incorrect. Perhaps the universe organized itself much faster than we ever imagined. However, the evidence of impossible timing is not limited to galaxy collisions. Next, something even more complex was discovered concerning the cosmic microwave background, CMB itself. The CMB can be compared to a baby picture of the universe, capturing its appearance just 380,000 years after the Big Bang. This ancient light bears the imprint of the tiniest density fluctuations, which were destined to evolve into the galaxies, stars, and everything we see today. However, observations made by the James Webb Telescope hint that this baby picture might be distorting the universe's developmental history. The cosmic microwave background presents a universe that, in its early periods, was remarkably smooth and uniform. Density variations were incredibly small, amounting to only 1 part in 100,000. These minute ripples in the cosmic fabric were like seeds that slowly grew under gravitational pull over billions of years, transforming into the large-scale structures observed today. Cosmologists have used sophisticated computer simulations to trace the growth of these seeds over time, aiming to accurately predict how the universe should look at any given moment. These models are incredibly detailed, tracking the clumping of dark matter, the flow of gas, and the formation of stars. According to these simulations, during the epoch observed by the James Webb Telescope, galaxies should be small, irregular, and relatively rare. But the reality proved different. The massive organized galaxies discovered by the James Webb require far larger initial density fluctuations than those recorded by the cosmic microwave background. This is akin to finding mature trees in a field where soil analysis indicates only grass seeds were planted. Dr. R.A. Manelli from the University of California, comparing James Webb's observations with the predictions of the cosmic microwave background, describes this discrepancy as a fundamental problem. It appears the early universe had a much greater capacity for structure formation than its baby picture suggested. This discrepancy is not minor. Some galaxies discovered by the James Webb are so massive that their formation would have required regions of space overdense to a degree that, according to cosmic microwave background data, should not have existed. The probability of such massive galaxies forming from the observed initial conditions is statistically close to zero. This creates a paradox that strikes at the very foundations of cosmology. Either the interpretation of the cosmic microwave background is flawed, or our understanding of how structures emerge from initial fluctuations requires a radical overhaul. Both options would necessitate abandoning fundamental ideas about cosmic evolution. Some theorists are exploring exotic solutions, including primordial black holes, modified gravity, or entirely alternative scenarios for the early universe. Others suggest that the cosmic microwave background might not be as pristine a record of initial conditions as previously thought. The mismatch between the cosmic baby picture and what the James Webb has found in the universe leads to an even more unsettling discovery about black holes growing at incredible rates. Quasars are the most powerful beacons in the universe, powered by supermassive black holes that consume matter at incredible rates and eject energy across billions of light years. These cosmic monsters contain masses millions or billions of times that of our Sun. However, the James Webb has discovered fully formed quasars shining at a time when the universe was so young that black holes should have barely begun their journey to such enormous sizes. Building a supermassive black hole is like constructing a skyscraper out of grains of sand. This process requires patience and a large amount of raw material. Even under ideal conditions, black holes can only grow at a certain rate, as the energy they release when accreting heats and pushes away the very matter they are trying to consume. This natural speed limit means that even the hungriest black holes require billions of years to reach supermassive dimensions. The laws of physics are relentless. As matter falls into a black hole, it heats up and glows brightly before disappearing forever. This radiation pressure acts like a cosmic traffic controller, limiting the amount of matter that can approach a black hole at any given time. The maximum growth rate, known as the Eddington limit, means that even a black hole starting with a mass of 1,000 suns would take over 1 billion years to reach a mass of 1 billion solar masses. Nevertheless, the James Webb has found quasars powered by black holes with masses of billions of solar masses when the universe was only 600 million years old. These are not modest black holes, still in the process of growing. These are fully formed supermassive objects, already dominating their galactic neighborhoods and powering some of the brightest objects in the cosmos. Dr. Xiaohui Fan from the University of Arizona, who studied these early quasars, compared their discovery to finding adult elephants in a nursery full of mice. The growth rates required to explain these observations exceed theoretical limits by 10 times or more. Either our understanding of black hole physics is incomplete, or these black holes were initially much larger than models predict. The discoveries concerning black holes become even more intractable when considering their initial origin. The very first black holes, logically, should have formed from the collapse of first-generation stars, which in turn required tens of millions of years to form and evolve. This means that so-called seed black holes, destined to eventually become supermassive, should have begun their lives with masses equivalent at best to 100 solar masses. However, making the transition from 100 solar masses to 1 billion solar masses in just 600 million years, while adhering to the Eddington limit, is mathematically an impossible task. This is like trying to drive from New York to Los Angeles in 1 hour while strictly obeying the speed limit. Some theoretical scientists hypothesize that the first black holes might have formed through entirely different mechanisms, starting with much more substantial initial masses. Others allow that black hole growth in the early universe might have occurred without being subject to the same physical limitations we observe today. Nevertheless, these incredibly massive black holes influence star formation. Stars are born in cosmic nurseries known as molecular clouds, where gravitational forces gradually compress gas and dust until nuclear fusion ignites. This process has natural speed limits inherent in the physics of matter's behavior under extreme conditions. However, the James Webb Space Telescope has discovered galaxies where stars are forming with such intensity that it violates all theoretical maximums calculated for star birth. In the modern universe, even the most active star-forming galaxies convert only about 1% of their gas supply into stars every million years. This efficiency limit is due to the chaotic and inefficient nature of star formation. As massive stars form, they begin to emit powerful energy flows, and at the end of their life cycle, they explode as supernovae, heating and dispersing the surrounding gas. This process, known as stellar feedback, functions like a cosmic thermostat regulating the rate at which new stars form. The most extreme star-forming galaxies we observe today produce about 1,000 new stars per year. This rate is already considered extraordinary and unsustainable. Galaxies forming stars with such intensity should deplete their gas reserves within a few 100 million years. Nevertheless, the James Webb Space Telescope has found early galaxies where the star formation rate exceeds 10,000 stars per year, and this activity is sustained for periods that seem impossible. Dr. Pascal Oesch from the University of Geneva, who analyzed these star birth rates, describes them as finding cosmic factories operating at 10 times maximum capacity. The energy released from such intense star formation should heat and expel all remaining gas, virtually immediately ceasing further star birth. Yet, these galaxies apparently maintain extreme star formation rates for hundreds of millions of years. The physics becomes even more complicated when considering the raw materials required. Forming 10,000 stars per year demands gas consumption at such a rate that even the largest reservoirs would be depleted in an instant. These galaxies would have needed a constant resupply of fresh material from their surroundings. However, the early universe was much less dense than the modern one, making such large-scale gas flows unlikely. Even more puzzling is how these galaxies managed to retain their star-forming gas at all. The intense radiation produced by rapid star formation should have created powerful galactic winds that completely blew the gas out of the galaxy. We can observe this process in local starbursts, where stellar feedback eventually suppresses the formation of new stars. However, these early galaxies appear impervious to their own stellar violence. This discovery suggests that star formation in the early universe operated under entirely different rules than those we observe today. Perhaps the gas was denser, stellar feedback was less effective, or the entire star birth process was fundamentally different when the cosmos was young. Some astronomers propose exotic mechanisms involving primordial gas with unusual properties, or gravitational conditions that no longer exist in the modern universe. Others suggest that our understanding of stellar feedback and gas dynamics needs a serious revision. However, these impossible star formation rates are organized into structures that challenge our understanding of cosmic evolution itself. The early universe, according to conventional understanding, was a chaotic and turbulent space where matter collided randomly under the influence of gravity, striving to order the aftermath of the Big Bang. The large-scale structure of the cosmos was believed to form slowly and haphazardly over billions of years through countless collisions and mergers. However, discoveries made by the James Webb Space Telescope indicate a high level of cosmic organization, suggesting that the universe had a clear blueprint for its evolution from the very beginning. Imagine the cosmic web, a three-dimensional network spanning billions of light-years, where galaxies are arranged along filaments of dark matter like dewdrops on silken threads. This web-like structure is one of the most impressive and organized features of the modern universe. Computer simulations show that forming such ordered structures from homogeneous initial conditions after the Big Bang requires at least 1 billion years. Nevertheless, the James Webb Space Telescope provides us with hints of large-scale structure and an organized distribution of galaxies during the epoch of cosmic dawn, when the universe was only a few 100 million years old. We observe aligned clusters of galaxies, coordinated star formation patterns over vast distances, and gravitational interactions between objects that should, theoretically, have remained isolated in space. Dr. Casey Papovich from Texas A&M University describes these early large-scale structures as finding a completed puzzle when expecting to see scattered pieces still looking for their place. The level of gravitational coordination between distant objects indicates that the cosmic web developed much faster than our models predict. Organization is evident across different scales simultaneously. Not only do individual galaxies possess more structure than expected, but they are also grouped into clusters and groupings that should not have had time to form. The gravitational binding energy required to hold such systems together suggests they formed much faster and more efficiently than is possible within hierarchical structure formation. Even more astonishing is how these organized structures maintain their coherence over such vast distances. In the early universe, light had not had enough time to travel between widely separated regions, meaning they could not coordinate their behavior through any known physical mechanisms. Nevertheless, we observe interconnected properties on scales that should, theoretically, be causally disconnected. This problem of cosmic organization challenges fundamental ideas about how the universe evolved from homogeneous initial conditions to the structured cosmos we observe today. If large-scale structure formed so rapidly, it points to processes or initial conditions different from those predicted by the Big Bang theory. Some cosmologists are exploring ideas about cosmic phase transitions, primordial magnetic fields, or exotic forms of dark energy that could have accelerated structure formation. Others question whether the initial conditions after the Big Bang were as homogeneous and random as we assumed. However, this organized cosmic architecture supports planetary systems that formed incredibly early in cosmic history. The formation of rocky planets, like Earth, requires a cosmic recipe that takes billions of years to prepare. Several generations of stars are needed to create heavy elements, supernova explosions to scatter these elements into space, and then slow gravitational processes to coalesce dust and debris into solid worlds. However, the James Webb Space Telescope has found evidence of planetary systems in galaxies so young that the ingredients for rocky planets should not yet have existed. Planet formation can be compared to cosmic cooking that cannot be rushed. The first stars consisted only of hydrogen and helium, the simplest elements created by the Big Bang itself. Every heavier element, the carbon in our bodies, the oxygen we breathe, the silicon in Earth's rocks, the iron in our blood, had to be produced within stellar cores and dispersed as a result of stellar death. This element production takes time. Even after heavy elements become available, building planets is a slow process. Tiny dust grains must stick together to form pebbles. Pebbles coalesce into boulders, boulders accumulate into asteroids, and asteroids collide to build planets over tens of millions of years. The entire sequence from stellar death to rocky planet formation typically requires at least 1 billion years of cosmic evolution. Nevertheless, spectroscopic analysis of some early galaxies shows absorption features that may indicate the presence of dust and possibly even planetary debris in systems that formed when the universe was less than 800 million years old. Dr. Kevin Heng from the University of Bern describes these observations as finding evidence of planetary construction in a cosmic era when building materials should not yet have existed. The implications of these discoveries profoundly impact our understanding of when life might have first appeared in the universe. If rocky planets could form so early, then conditions for biology might have existed billions of years sooner than we ever imagined. Perhaps the universe was teeming with potentially habitable worlds when our own solar system was still just a distant dream. Even more captivating are the hints of atmospheric absorption in some of these earliest planetary systems. While it is still premature to definitively claim the detection of planetary atmospheres around such distant and ancient objects, spectral data point to a complex chemical composition, including heavy elements arranged in a way that suggests atmospheric processes. This discovery forces scientists to reevaluate the speed at which planetary systems form and begin to function as complex chemical laboratories. Perhaps dust particles coalesced more efficiently in the early universe, or gravitational processes proceeded faster in the denser environment of the young cosmos. Some astronomers suggest that the first planetary systems might have formed through mechanisms not observed in the modern universe, possibly involving primordial materials or gravitational conditions that no longer exist today. However, these rapidly forming planetary systems challenge the very understanding of cosmic inflation theory. The theory of cosmic inflation posits that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, stretching space faster than the speed of light and smoothing out any initial inhomogeneities. This inflation was presumed to have created a universe with very specific properties, smooth on large scales, with tiny, precisely characterized fluctuations that slowly grew into cosmic structure. However, the James Webb Space Telescope's discoveries suggest that the universe may not have followed the inflation scenario. Inflation theory makes testable predictions about what the early universe should look like. The density fluctuations that eventually became galaxies should have had specific statistical properties, following patterns reflecting the quantum mechanical processes that created them during the inflationary epoch. These fluctuations should be small, nearly scale invariant, and distributed according to precise mathematical relationships. The problem is that the massive organized structures discovered by the James Webb Space Telescope require much larger and more organized initial fluctuations than inflation theory predicts. The theory suggests that regions of space dense enough to form the observed massive galaxies should be extremely rare. So rare that scientists should not observe any in the cosmic volumes accessible to the James Webb Space Telescope. Dr. Paul Steinhardt from Princeton University, one of the creators of inflation theory who later became its critic, describes these observations as potentially fatal problems for the inflationary paradigm. The statistical properties of early galaxies do not match what inflation theory predicts should arise from quantum fluctuations during exponential expansion. Even more problematic is the coherent organization of structure on vast scales. Inflation theory predicts that different regions of space should have evolved independently after rapid expansion separated them beyond any possible causal connection. Nevertheless, the James Webb Space Telescope's observations hint at coordinated properties over distances that should be entirely independent according to inflationary cosmology. This discovery forces cosmologists to confront uncomfortable questions about whether cosmic inflation truly occurred or if it operated differently than existing models suggest. Alternative theories that never required inflation are once again gaining attention as potential explanations for the James Webb Telescope's observations. Some theorists are studying bouncing universe models, where the cosmos emerged from the collapse and rebound of a previous universe, potentially preserving organizational information that inflation would have erased. Others are exploring theories of modified gravity or exotic forms of dark energy that could create the observed structure without requiring inflationary expansion. The implications of these investigations extend far beyond cosmology and touch upon fundamental physics. Inflation theory has been closely linked to theories of quantum gravity in the earliest moments of cosmic history. If inflation is incorrect, it suggests that our understanding of physics at the most fundamental level needs a serious reevaluation. However, as numerous independent observations point to the same problems, this evidence becomes impossible to ignore. Scientific progress rests on the gradual accumulation of evidence, and isolated anomalies that deviate from the general picture are often explained by measurement errors, statistical deviations, or gaps in understanding. However, when numerous independent observations obtained using various methodologies converge to point to the same fundamental problem, the scientific community is forced to acknowledge the possibility that accepted theories may simply be wrong. The discoveries made with the James Webb Space Telescope represent precisely such a crisis of converging evidence. This telescope has found not just isolated anomalies, but an entire spectrum of inconsistencies. Massive galaxies where only small formations should have been, heavy elements forming at an incomprehensible rate, ordered structures that should, in theory, have been chaotic, rotation speeds that defy the laws of physics, signs of collisions preceding interactions, star formation rates exceeding theoretical limits, and planetary systems formed with incredible rapidity. Each of these discoveries individually could be dismissed as a fluke, but collectively, they paint a picture of a universe that does not adhere to the rules we know. Independent research groups, applying various analytical methods, have repeatedly confirmed these findings. The galaxy mass measurements conducted by Dr. Evo have been re-verified by several groups using entirely different approaches. Spectroscopic data on early heavy elements have been confirmed in multiple independent studies. The impossible rotation speeds have been validated by both direct speed measurements and gravitational lensing studies. Even more compelling is the fact that all these diverse anomalies point in one direction, towards a universe that organized itself much faster and more efficiently than the Big Bang theory predicts. The emerging problems are not random, scattered discrepancies that could be explained by minor adjustments to the theory. They form a coherent picture, indicating that our fundamental timeline of cosmic evolution is flawed. The statistical significance of the accumulated evidence is becoming overwhelming. When astronomers try to estimate the probability that all these observations can be explained by measurement errors or rare statistical fluctuations, the resulting numbers are vanishingly small. This is not about random coincidences, but systematic discrepancies that demand an explanation. Such a convergence of evidence is forcing theoretical physicists to abandon gradual modifications of existing theories and consider revolutionary alternatives. Dr. Subir Sarkar from Oxford University characterizes the current situation as a paradigm crisis, where accumulated anomalies can no longer be explained within the existing theoretical framework. This process resembles historical scientific revolutions, where numerous independent observations eventually led to a complete overhaul of theories. Just as the discovery of stellar parallax, galactic redshifts, and the cosmic microwave background radiation once converged to establish the Big Bang theory, the James Webb Space Telescope's discoveries may lead to its overthrow. Scientific institutions are beginning to realize that the discovered discrepancies require serious theoretical consideration, not just ad hoc explanations. Major organizations funding scientific research are allocating resources to develop alternative cosmological models that could explain the James Webb Space Telescope's observations without violating fundamental laws of physics. The accumulated body of evidence is pushing theoretical physicists to create entirely new models of cosmic evolution. Behind closed doors in physics departments worldwide, scientists are feverishly working to develop alternative cosmological models that could explain the impossible observations of the James Webb Space Telescope without violating the laws of physics. This is not about minor adjustments to existing theories, but about revolutionary new concepts that could completely replace the Big Bang theory. The hidden urgency with which this theoretical work is being conducted reflects the seriousness with which physicists are treating the growing crisis of evidence. Dr. Neil Turok of the Perimeter Institute is developing models of cyclic cosmology, in which the universe undergoes endless cycles of expansion and contraction, with each cycle preserving organizational information that could explain the rapid structure formation observed by the James Webb Space Telescope. These models suggest that our universe may not have had a beginning at all, but rather emerged from the organized collapse of a previous cosmic cycle. Meanwhile, Dr. João Magajo of Imperial College London is delving into cosmological models with a variable speed of light, where fundamental physical constants exhibited different values in the dawn of the universe. The hypothesis of faster light propagation in the cosmos's youth could have provided coordinated evolution between widely separated regions. This might explain the large-scale organization discovered by the James Webb Space Telescope without needing to invoke unrealistic timescales. Theorists working on modified gravity, such as Dr. Sabine Hossenfelder, question whether gravitational physics obeys different laws on cosmic scales or under extreme conditions. If gravity was more potent or acted through extra dimensions in the early universe, structure formation could have occurred significantly faster than predicted by general relativity, naturally explaining the mature galaxies found by the James Webb Space Telescope. Even more radical are theories allowing for the existence of multiple universes or higher dimensional physics. Some models suggest that the observable part of the cosmos might be embedded within a larger multiverse structure, where matter and energy move between connected regions through mechanisms we have yet to understand. Such scenarios could provide the additional organizational force needed to explain rapid cosmic evolution. Dr. Paul Frampton from the University of North Carolina is exploring bouncing cosmologies, where dark energy cyclically transitions between phases of expansion and contraction, giving rise to periods of accelerated structure formation, which could explain the James Webb Telescope's observations. These models reject the idea of a single Big Bang in favor of multiple cosmic epochs with varying physical properties. Theoretical investigations are proceeding with unprecedented urgency as observational data continues to accumulate faster than explanations can be developed. Each new discovery from the James Webb Space Telescope adds constraints, ruling out more traditional explanations and pushing theorists to seek increasingly exotic alternatives. The particular significance of this theoretical revolution stems from its simultaneous unfolding across multiple subdisciplines. Cosmologists are revising models of cosmic evolution, particle physicists are questioning fundamental constants, and astrophysicists are reevaluating processes of stellar and galactic formation. The crisis triggered by the James Webb Space Telescope's discoveries is spurring a coordinated rethinking of the foundations of physics. Among the most promising new models is the concept physicists call emergent gravity, the idea that gravitational attraction may not be fundamental, but arises from more basic quantum mechanical processes. If gravity operates differently than we presumed, it could explain why cosmic structures form significantly faster than current theories predict. However, these new theoretical frameworks are approaching a tipping point where they can fundamentally alter our understanding of time and space themselves. Albert Einstein's theory of relativity taught us that space and time are interwoven into a single fabric called spacetime, which can stretch, curve, and warp under the influence of matter and energy. This understanding has been repeatedly confirmed and forms the bedrock of modern cosmology. Nevertheless, the James Webb Space Telescope's discoveries compel physicists to question whether spacetime itself functions differently than we assumed, especially under the extreme conditions of the early universe. The problem is not just that galaxies formed faster than expected, but also that they formed in a way that seemingly violates causality itself. Structure formation requires information exchange between different regions of space so they can coordinate their gravitational behavior. However, in the early universe, many of the organized structures discovered by the James Webb Space Telescope are separated by distances that light would not have had time to traverse, making coordination impossible within our current understanding of spacetime. Darley Smolin of the Perimeter Institute is exploring theories in which time itself may be emergent rather than fundamental. In these models, what we perceive as the flow of time might be only an approximate description that loses its adequacy under extreme conditions. If time functioned differently in the early universe, it could explain processes that seem impossible within modern physics. New discoveries made with the James Webb Space Telescope are forcing scientists to rethink established notions of space and time. Some theorists suggest that space might possess extra dimensions that were accessible in the early universe, but have since become hidden. Models with extra dimensions could explain how information and energy moved faster than the speed of light in our three-dimensional space, accounting for the impossible coordination observed by the James Webb Space Telescope. Some scientists are investigating the possibility of a variable speed of light throughout cosmic history. If light traveled faster in the early universe, it would allow distant regions to interact and coordinate their evolution, explaining the large-scale organization that formed too quickly within the framework of modern physics. Dr. Carlo Rovelli from the French National Center for Scientific Research has developed theories of loop quantum gravity, where spacetime itself is quantized and composed of discrete units. In such models, the structure of spacetime could behave differently under the extreme conditions of the early universe, allowing for structure formation processes impossible in classical spacetime. These implications extend beyond cosmology and touch upon the nature of reality itself. If our understanding of time and space is flawed, it affects everything from quantum mechanics to the possibility of time travel. The James Webb Space Telescope's discoveries may indicate that the universe operates according to physical laws we have yet to uncover. These spacetime theories point to the possibility that the Big Bang might not have been the beginning of everything. For almost 100 years, the Big Bang theory was not just a scientific concept, but our origin story, the answer to where everything came from. However, the James Webb Space Telescope's discoveries force us to consider that the Big Bang might not have been the beginning of everything, but merely one event in a much larger cosmic history that we are only beginning to comprehend. The evidence suggests that the universe was already organized and structured before the Big Bang. The massive galaxies, heavy elements, and coordinated structures discovered by the James Webb Space Telescope indicate that cosmic evolution did not start from a homogeneous state. Instead, they hint that the universe inherited organizational information from a previous stage. Dr. Anna from New York University is developing models where the Big Bang arises from the collapse and rebound of a previous universe. In these scenarios, the organized structures observed by the James Webb Space Telescope could be fossils of cosmic evolution preceding our current expansion phase. The universe may undergo endless cycles of expansion, contraction, and rebirth, with each cycle preserving information from the previous one. Even more revolutionary are theories suggesting that multiple universes might exist simultaneously, exchanging matter and energy through mechanisms we do not yet understand. If our observable universe is connected to a larger multiverse, this could explain where the organizational force for rapid structure formation came from. It could have been borrowed from neighboring universes. Some physicists are investigating the possibility that the Big Bang was a phase transition rather than an act of creation. Just as water can transition from solid to liquid to gas while remaining the same substance, the universe might have transitioned from one physical state to another without beginning to exist. Dr. Abhay Ashtekar from Pennsylvania State University has developed models of loop quantum cosmology where the Big Bang is replaced by a big bounce, a transition from a phase of contraction to a phase of expansion in cosmic evolution. In these models, the universe has neither a beginning nor an end, but undergoes eternal cycles of expansion and contraction. The philosophical implications of these theories are immense. If the Big Bang was not the beginning of everything, then questions about what came before it become scientifically significant, not just metaphysical musings. The universe may be infinitely old, and our current phase of expansion merely one chapter in its eternal history. This possibility challenges not only cosmology, but also our understanding of causality, existence, and the nature of reality itself. If the universe has always existed in some form, it changes our perspective on everything, from the origin of physical laws to the possibility of life in previous cosmic cycles. The James Webb Space Telescope's discoveries may indicate that we are not the first chapter of cosmic evolution, but perhaps just the latest chapter in an endless book. A genuine scientific revolution is brewing in the world of cosmology, and it's not merely about adjusting minor details or fine-tuning existing theories. The discoveries made possible by the James Webb Space Telescope have brought us to a critical point where accumulated evidence may force scientists to completely abandon the current story of cosmic origin and embrace something entirely different. Humanity now stands on the threshold of a paradigm shift that, in its scale and significance, could well rival the revolution ushered in by Nicholas Copernicus. The tipping point arrives when anomalies can no longer be explained by simply modifying existing theories. In the history of science, such a moment occurs when numerous independent lines of evidence converge on the same conclusion. The fundamental assumptions underlying the accepted theory are simply wrong. And the James Webb Space Telescope's discoveries are rapidly approaching this critical mass of contradictory evidence. Dr. Subir Sarkar, representing Oxford University, characterizes the situation as an epic crisis in cosmology. The modern standard model of cosmic evolution requires increasingly exotic modifications to somehow fit each new observation made by the James Webb Space Telescope. Dark energy, apparently, must be much more complex. Dark matter must behave completely differently. Inflation must work in ways no one could even imagine. And stellar physics in the early universe must obey entirely different rules. The mathematical contortions necessary to salvage the Big Bang theory are becoming so complex that many physicists are beginning to ask, isn't it time to completely abandon this theory, rather than continuing to patch it with increasingly implausible modifications? A point is reached when the cure becomes worse than the disease. Influential scientific organizations are beginning to acknowledge the full gravity of the unfolding crisis. The European Space Agency has already approved funding for missions specifically designed to test alternative cosmological models. The U.S. National Science Foundation has created new funding categories for research into non-standard cosmologies. Such a response from major institutions reflects a growing awareness that the James Webb Space Telescope's discoveries represent more than just interesting anomalies. The convergence of evidence is constantly accelerating. Almost every month, new observations made by the James Webb Space Telescope add to the mountain of unexplained data. The statistical probability that all these anomalies can be explained by measurement errors or theoretical oversights approaches zero. The universe revealed by the James Webb Space Telescope simply does not conform to the universe predicted by current theories. Historical experience suggests that humanity is approaching a moment when the scientific community will be forced to choose between increasingly implausible explanations for existing theory and revolutionary new models that naturally explain all observations. Ptolemy's system of planetary motion required increasingly complex epicycles to match observations, until Nicholas Copernicus proposed that the Sun, not the Earth, was at the center of the solar system. Humanity may now be witnessing a similar moment in cosmology. The Big Bang Theory demands increasingly complex modifications to somehow align with the James Webb Space Telescope's observations. Alternative theories, which seemed radical just a few years ago, now appear to be quite natural explanations for what people are actually seeing. It is highly probable that the next few years of observations made by the James Webb Space Telescope will determine whether humanity stands on the verge of the end of the Big Bang era in cosmology and the beginning of something entirely new. The story of the universe's origin is not just a scientific theory. It is the foundation for understanding our place in the cosmos itself. If the discoveries made by the James Webb Space Telescope compel people to abandon the Big Bang Theory and adopt an entirely different cosmic origin story, the consequences will cascade through all aspects of human knowledge. Throughout history, shifts in humanity's cosmic narrative have triggered profound changes in human consciousness, affecting everything from philosophy and religion to the most basic sense of meaning and purpose. When Nicholas Copernicus demonstrated that Earth was not the center of the universe, it changed more than just astronomy. It sparked a true revolution in philosophy, religion, and humanity's sense of its own significance. When Charles Darwin showed that life evolved rather than being specially created, it transformed not only biology, but also the entire understanding of what it means to be human. The revolution associated with the James Webb Space Telescope promises to be even more fundamental. If the universe has always existed in some form, without a definitive beginning, it challenges fundamental assumptions about causality, creation, and the nature of existence itself. Questions that have driven human inquiry for millennia. Why is there something rather than nothing? What came before the beginning? What is humanity's cosmic purpose? Will require complete re-evaluation. Dr. Carlo Rovelli from the French National Center for Scientific Research asserts that major scientific revolutions always force people to reconstruct their understanding of reality from the ground up. The discoveries made by the James Webb Space Telescope challenge not just cosmology, they challenge the conceptual frameworks people use to comprehend existence itself. If the universe operates according to physics that humanity has yet to discover, and if time and space work differently than people assumed, then this opens up possibilities that are currently hard to even imagine. Perhaps consciousness plays a role in cosmic evolution. Perhaps information is more fundamental than matter and energy. Perhaps the universe is far stranger and more wondrous than current theories suggest. The discoveries made with the James Webb Space Telescope have far-reaching consequences, affecting even the very possibility of life. If rocky planets and complex chemical compounds emerged billions of years earlier than anticipated, it is quite possible that the universe was teeming with life at a time when our solar system was still just forming. It is entirely possible that we are not the first intelligent beings to ponder the cosmos, but rather the latest in an incredibly long chain of cosmic evolution. Even our understanding of death and time may undergo changes. If the universe passes through eternal cycles of expansion and contraction, preserving information throughout all cosmic phases, then this raises serious questions about whether anything can truly disappear forever. The discoveries made by the James Webb Space Telescope may point to a universe where existence itself is eternal and indestructible. Psychological adaptation to an entirely new cosmic history will be a challenging task. Humans have always needed origin stories to give meaning and context to their lives. The Big Bang Theory, for all its scientific precision, also served as a kind of modern creation myth, helping people understand their place in cosmic space. Perhaps, however, the most important implication is that the James Webb Space Telescope's discoveries remind us how much more we still have to learn. The universe continues to surprise us, revealing new mysteries just when we begin to think we've understood everything. The most significant discovery may turn out not to be any specific new theory, but rather the humble recognition that the cosmos is far stranger, more complex and more astonishing than we ever could have imagined. The James Webb Space Telescope was built to confirm our understanding of cosmic origin, but instead, it is perhaps showing us galaxies that, according to our theories, should not exist, stars forming too quickly, and structures that possess excessive organization for such a young universe. The telescope that was meant to be the star witness for the Big Bang Theory may well be writing its obituary. The evidence gathered by the telescope is astounding and undeniable. Massive galaxies in their early stages of development, heavy elements formed at an incredible rate, rotation speeds that defy the laws of physics, signs of collisions that occurred before interactions were thought possible, star formation rates exceeding theoretical limits, and planetary systems that formed before the necessary components should have existed. Each of these discoveries could be explained individually, but collectively, they paint a picture of a universe that refuses to obey our established rules. This is not merely a crisis in cosmology, but a revolution in our understanding of reality itself. The accumulated data from the James Webb Space Telescope is forcing physicists to question not only when the universe originated, but whether it had any beginning at all. We may be witnessing the twilight of the Big Bang era and the dawn of an entirely new cosmic history. The implications of these discoveries affect every aspect of human knowledge. If time and space function differently than we assumed, if the universe has always existed in some form, if cosmic evolution adheres to laws of physics we have yet to discover, then everything we knew about existence requires re-evaluation. The questions that have driven human inquiry for millennia must be rethought. But perhaps the most important discovery lies in how many mysteries still remain to be solved. The universe continues to amaze us, revealing new wonders just when we begin to think we've understood everything. Observations made with the James Webb Space Telescope remind us that the cosmos is far stranger, more complex, and more astonishing than our theories suggest. The most significant scientific revolutions in history began with observations that did not align with existing theories. Nicolaus Copernicus, Charles Darwin, Albert Einstein, all started by uncovering facts that forced humanity to reconstruct its understanding of reality from the ground up. The discoveries made by the James Webb Space Telescope could mark the beginning of a similar revolution that will transform not only cosmology, but our entire conception of existence itself. We are on the verge of a new cosmic history that may show the universe to be eternal, infinite, and far more mysterious than we ever could have imagined. The telescope, built to confirm our origin story, may instead be opening the first chapter of an entirely new book of cosmic understanding. The most thrilling discoveries are still ahead, awaiting their moment in the light of ancient galaxies that refuse to obey our established rules, in the rotation of impossible stars, and in the organization of a universe that seems to have known exactly what it was doing from the very beginning. The story of how the universe came to be is not over. It is only just beginning to be told. Friends, if you enjoyed our video, please don't forget to like and subscribe to the channel. Thank you for watching.